Hello student, I am Arnab Das. Today we discuss about the multi-stage transistor amplifier. When the voltage amplification or power gain of a single stage amplifier is insufficient to meet the requirement, then multi-stage transistor amplifier is used. That means if their minimum number of two stages is present, that time this kind of amplifier will be defined as a multi-stage amplifier. And obviously, in between this minimum two stage, there are an extra thing you have to add it on there, which are required for the coupling between these two stage, and these are defined as a coupling device. Ultimately, the output due to this multistage, there the voltage gain will be defined the effect of individual voltage gain into the product form. Let if we consider the for the first stage, the voltage gain is defined by the AV1, and for the second stage, the voltage gain is defined by the AV2. That time, total voltage gain will be defined as the AV1 multiplied with the AV2. And as we know that voltage gain, that is AV, is defined as the output voltage by of input voltage. So if you consider for the AV1, that time that the output voltage is defined the V2, if this position is defined the V2 as the output voltage. So this is V2 by of V1, and therefore the second stage the AV2 will be defined as a V0, which is the output, and V2 in this case is the input one. So this is V2. So ultimate output will become on there for the multi-stage amplifier will be AV is equal to as a value of V0 by of V1. So what will be the purpose for the coupling device then? The transfer AC output of the one stage to the input of the next stage. This is one of the most prime purpose for the coupling device. Second one is that to block the DC to pass from one stage to the next stage. That is to isolate the DC component. What type of coupling device you are choosing on that point of view? There are basically four types. First one is defined as the RC coupling circuit. For the RC coupling circuit, the resistor and capacitor are used for the coupling component, and combined of this circuit will be defined the coupling device for RC couple amplifier. So again I just repeat that coupling circuit is required for the multi-stage amplifier which interlink between the two stage. In this case, here the resistor and capacitor are used, and for this reason it is defined as a RC couple or coupling amplifier. Another kind will be defined as a impedance coupling. When the amplifier, this coupling is known as the coupled amplifier. The coupling network consists of inductance and capacitance. The previous case, it was the resistor and inductor. In this case, capacitor and inductance. These two are used for coupling one. Third one form is the transformer coupling, where the transformer is used for the requirement of the coupling between these two stages. And last one is that direct coupling, where directly coupled with these two amplifier. Initially we just talk about the RC coupled amplifier. This is the most important one also. Look that the highlighted portion is defined for the biasing circuit 1. Look at this is the biasing circuit 1. This is the biasing circuit 1. So same circuit is repeated on here also. This is the same circuit is repeated in here also. In between the capacitor and for the first stage the output RL, the combined effect will be defined the RC coupled for this multi-stage amplifier. For the RC coupled amplifier, there the equivalent circuit can be drawn in this way, where we assume some condition by which the equivalent circuit is simplified on that. First one is that there R1 and R2 for stage 1 or 2, R1 and R2 can have to choose in such a way the parallel effect of R1 R2, this one in this case figure you just check on here, this R1 and R2 you have to choose in such a way that in the equivalent circuit position the parallel form of this R1 R2 will be so high impedance, and that means it will be work just like as an open circuit on there. And there H of OE for the transistor, that is the transistor parameter which is come at the output section side, you have to choose the transistor in such a way H of OE is so small, that means the admittance term, that is 1 by of H of OE, this value will be also the so high impedance and it will be work just like as a open circuit on there. And for this reason this is represent as such. And the input side, that induced voltage which is defined the H of which was present in this position, H of RE of V of 2, if the 2 is the output voltage. So H of RE you have to choose in such a way, this is so small, that means the induced voltage will be also so small and it will be work just like as a short circuit. So what are the assumption? I just read out this one again on here. First one is that H of RE is so small. Second one is that A 1 by of H of OE will be so large. The reactance C in any given input frequency is so small that the parallel combination of H of RE and C can be effectively considered as a short circuit. And the biasing resistor R1 and R2 will be used as a so large form. So these are the assumption you have to take on there. So for the first stage, this is the section, and here the capacitor is the coupling one, and this side is the another one. This will be the repeated on there. That means H of I will become again in this position as the first stage. Then it will be the induced current source will become in this position. So this is repeated on here. So we just concentrate in this position by which our analysis can be proceed. For the amplifier circuit 1, their AC signal will be induced and the output also will be the AC one. For AC signal, there should be the frequency parameter will be present. And for any kind of circuit, there some limitation is present. That means there some maximum frequency and there's some minimum frequency in between the amplification process done properly. So we have to identify for any kind of RC couple of amplifier how you can also define this one. So for this reason, initially we just consider again just repeat this one. For any kind of circuit, if we consider this is the frequency term, this is the frequency term, and this is the amplifier one or amplification done on there. So if it is the low frequency value, that time the amplification is not proper, that is properly amplification not occur on there. And if it is the high frequency position or cut frequency for the higher, value. So in between, the amplification is done properly, and after that it will be again they are due to the high frequency amplification not done properly on there. So this is the mid frequency zone. Let this is the small m mid frequency zone. This is the low frequency zone, and this is the high frequency zone. So this three section is present on there. In between the low frequency and mid frequency, they are differed by the lower cutoff frequency, and mid frequency and high frequency they are differed by higher cutoff frequency. So we have to get their three region for any kind of amplifier with respect to the frequency one. So it is the mid frequency, one is the high frequency region, and second one or third one is defined the low frequency region. So initially we just talk about the mid frequency region or mid frequency range. So in this mid frequency range, due to the reason of the high frequency, their capacitor will be work just like as a short circuit, because we know that Xc is equal to 1 by of 2 pi Fc. So here if the frequency value is rise up, that time the Xc impedance value for the capacitor will be low on there. So that means it will be work just like as a short circuit one. So what will be the equivalent circuit one for that case? Here capacitor will be as a short circuit one. So from this circuit we can got the equivalent Thevenin circuit, where this current source and the resistor will be multiplied to get the voltage source, and R is used for the series one to represent the source impedance value. So from this Thevenin equivalent circuit you can got that by using the KVL this section, for this section you can be able to got that H of FEIBRL is equal to I into RL. This is I into RL plus of H of I into RL, because the input voltage should be equal to the sum of the voltage drop across RL, voltage drop across the H of I. So you just use this two equation, use this KVL equation, and then you can got that expression, this one, that is V0 will be defined for that case. V0 will be defined that case, this one, because I is defined from this KVL, I is defined this one form. This is I is defined. Look that H of FEIBRL into I, sorry, H, this is the voltage source. This is H of FEIBRL is equal to I into RL plus of I into H of I. So from this you can got the value for the I. So I is equal to this one. Now you just put this value in this position to get the current gain on there. So current gain is defined the output current by the input current. So for this circuit the output current is defined the I. So you calculate the value for the I, and input current is defined the I of B. So from this you can write down this one. You just put the value for the I in this position, and then IB. So what will be the IB at the RA, the upper side will be omitted on there. So ultimate expression for the current gain will become as a minus of H of FERL by of RL plus of H of I. So what will be the magnitude on there? So this will be the mod value of this current gain. So minus will be omitted on there. Now for the voltage gain, it will be defined the V0 Y of Vi. For the V0, here output voltage is defined the H of I into of I. So this is, and you just put the value for the I, and I value is defined the minus of H of FE IB RL by of RL plus of H of I. You just put this value. So ultimately the expression will become this one. And for the input side, the voltage drop will be defined. The impedance values for the input side is the H of I. So H of I will be multiplied with the input current, that is the I of B. So the expression will become V of I is equal to H of I into of IB. Now to get the value for the voltage gain, you just put the value for the V0 and Vi, which is already derived by you. So this expression will become as a form of this one, and the magnitude will be as a mod value of AVM, and this will be omitted the minus sign. So from these two expression for the AV, here the suffix M is defined for the mid frequency region. Okay, so for the voltage gain and the current gain, both cases for the mid frequency region, the magnitude will be same one, and the phase change will be 180 degree, because the negative sign shows the phase change. Okay, so this is for the mid frequency region. Now for the low frequency region, what will be? For the low frequency, their capacitance, due to the capacitor, there the impedance value should be maintained on there, because xc is equal to 1 by 2 pi of fc. So in this case, f is so low, so you should consider the xc value, that is the impedance value. So in this case, you just consider this one. And what will be the equivalent circuit for this case now? The Thevenin equivalent circuit, this is the current source, this is the resistance value. So you just product these two, then the voltage source will be generated on there, and the RL you have to apply for the series to get the source impedance value. And now the capacitor is here, and this complete path will be given, or you can apply the KVL in this position. If you apply the KVL value in this position, that time what will be the expression for the I? Here I will be defined, as a value of, here voltage is the value of H of FVIB RL. So you just put this one value, and then there the value for the RL across voltage will be the RL into of I. So this is RL, this is J by of omega C due to the region of capacitor, and H of I is this one section. So current is defined this one value. The same process you can apply to get the value for the low frequency. So this will be defined the output current I by of IB. So this is value will be ultimate come this one, and here the magnitude will be defined for the low frequency AV of I. This is not written in here, so it will be written as such, the form of mod value. This is mod value will be defined as a value of minus, if you just got the mod value, so that time it will be defined as a H of Fe R of L by of root over of, this is this portion square, plus of 1 by omega c whole square. So this will be the magnitude for the current gain. Same way you can calculate for the voltage gain also. So voltage will be gain will be defined the resistance value and the current. So resistance value is there H of I. Look that this is the resistance value is H of I. So H of I will be multiplied with the current I. So you just put the value for the I on there. So you already know the value for the I, this one. You just put in this position the I value. So if you product these two, the ultimate expression will become for the voltage at the output side will be this one. And the input voltage is defined the H of I into of I of B. So you can got this one, and the for the low frequency, here the suffix L is defined for the low frequency region. here also define the low frequency region. So their AVL will be defined output voltage by of input voltage. So put the value and ultimately you got the value for the low frequency region, the voltage gain, and that one will be the minus of h of minus of h of Fe RL by of h of I plus of RL minus of J by of omega C. The what will be the magnitude? Magnitude will be defined as a h of Fe RL and then root over of this section square plus of 1 by omega c square, and omega is defined the 2 pi f. So this is written in this position 2 pi f c. So this is the total one squared. So this one the expression for the low frequency region, that the amplitude and also uh, for the voltage gain and also the current gain. Now you just concentrate for the high frequency range. For the high frequency range, their capacitor will be omitted on there. Look that their capacitor is omitted on here, but due to the Miller effect in the transistor itself, their capacitance value will be represented, because for a transistor, for a transistor, if you consider into the form of the block one, so there are three sections is present. One is the emitter side, second one is the base side at the middle position, and third one is the collector side. So in between the emitter and base, their depletion region create, and due to this depletion region, their two side is the charge particle. It will work just like as a capacitor one. So it is defined as a capacitor C of Be, and here also dielectric material or this their depletion region create between the base and collector region, and other two side is the charge particle region. So it also will be work as a form of the capacitor. So this is also defined as another kind of capacitance value. So this is defined the VC of BC. Due to the reason of this amplifier circuit is an emitter base are forward bias, so here capacitance value is so minimum 1, but uh, base and collector side it will be the reverse bias, so their capacitance value will be a higher one. Though due to the high frequency, this each and every capacitance value will be the combined form, and it will be work as a shunt capacitance value form, and which is defined as a C of T, and it should be considered as a shunt form with the input impedance H of I. So the equivalent circuit you got it in here, and from this you can able to identify the Thevenin equivalent circuit. For the Thevenin equivalent circuit, here in this case the current source is this one, so it will be multiplied with the RL, and also this is the parallel combination of this. So these two parallel combination will be multiplied to get the voltage source, and these two parallel combination will be defined the source impedance value. So from this you can got the ultimate Thevenin equivalent circuit, and you can apply now the KVL on there. So from this KVL you can calculate the value for the I, and from this I, if you ratio between I and IB, then the current gain you can able to identify, and if you identify the voltage drop across the CD due to the reason of the current I at the output side, and then ratio between the V0, which is due to the region of CD, by the V of I, that time you can got the voltage amplification factor, and from this voltage amplification factor you can also got it the magnitude one also. So this one is calculated in here. So in this case current is defined as this one by using the KVL, this one value. So you just put this value to calculate the current gain, and then the value will become on that. Look that only the IB is omitted on here, because this is the IB is in the numerator's denominator side. So current amplification factor will be this one, and the voltage at the output side will be the at the CD across what will be the voltage drop. So X C is defined the 1 by of j omega C. So in this case C is defined by the CD. So this is X will be this one, and it is multiplied with the I to get the output voltage. So I into 1 by j of omega CD, and you just put the value of I, which is already you got it from the equation number 13. So this value you just put it on here, and to get the ultimate expression for the V0 is this one value. Okay, and Vi already you know, this is multiplied with the input impedance with the input current. So this is Ib into of H of I. So ratio between them to get the value of the AV of H, and here H suffix is defined for the high frequency region, and the magnitude will be defined for the voltage gain will be defined value of as a value of h of FERE and root over of this real part square plus of imaginary part square. So this is omega is replaced as a 2 pi of f. So this is 2 pi of f CD h of I RL whole square. So I think each and everyone can able to identify for the RC couple amplifier how can you calculate the value for the current gain and voltage gain, and what will be the magnitude for the current gain and also the voltage gain. So uh, next day we talk about another kind of thing. Till I have to say have a good day and bye.